In a shocking astronomical discovery, the James Webb Space Telescope has unearthed 6 fully formed galaxies in an earlier time frame of the universe than anyone expected. The big answer so far is that the first galaxies grew differently than we thought, and we don't know why. With its towering gold-plated mirrors and deep space vision, Webb has once again stunned the scientific world. Recently, it peered into a seemingly ordinary patch of sky and found something that ignited a frenzy among physicists, cosmologists, and astronomers alike. What it revealed were massive, mature, fully formed galaxies that appear far earlier in the universe's history than current models of physics can explain. These galaxies are not supposed to be there, not at that time, not in that form, and not in such numbers. Their presence is nothing short of terrifying because it shatters the very frameworks scientists have been building for nearly a century. What Webb saw was more than a blur of ancient light. It was a window into a time barely 300 million years after the Big Bang, when the universe should still have been dark, chaotic, and just beginning to take its first structured breaths. Yet staring back from the depths of the early cosmos were galaxies brimming with complexity, spiral arms, heavy elements, mature star populations, and even supermassive black holes already formed at their centers. These were not fledgling clusters of gas and dust. They were structured, organized systems that should not have existed during what theory considers the universe's infancy. According to the Standard Model of Cosmology, grounded in Einstein's general relativity and the lambda-CDM model, the universe followed a predictable sequence. After the Big Bang, the cosmos cooled, then a few 100 million years later matter coalesced under gravity to form the first stars and protogalaxies. Over billions of years, those merged and evolved into spirals and ellipticals like the Milky Way. But Webb's images suggest that this process may have occurred exponentially faster, or differently, than we believed. The sheer mass of some of these early galaxies is astounding. One appears as massive as the Milky Way, yet it existed just 350 million years after the Big Bang. To build up so much stellar mass so quickly defies the limits of known astrophysical processes. Star formation should have bottlenecks, slowed by radiation pressure and supernova explosions, but these galaxies seem to have ignored those natural breaks entirely. Even more perplexing, some of these galaxies show signs of metal enrichment, meaning their stars had already gone through life cycles and produced heavier elements like carbon, oxygen, and iron. This suggests not only that the first generation of stars formed rapidly, but that they also lived, died, and seeded subsequent generations in impossibly short timescales. That alone points to an accelerated timeline of cosmic evolution, one that existing models cannot reconcile without invoking radical new physics. The real shock, however, comes from the presence of supermassive black holes at the cores of these primordial galaxies. Current wisdom holds that black holes grow slowly over time from the remnants of massive stars. Yet Webb has found some that are already millions or even billions of times the mass of the Sun within just a few 100 million years. To explain this, some theorists propose direct collapse black holes, entities forming instantly from giant clouds of gas without first becoming stars. But even those models strain under Webb's revelations. This discovery has thrown a wrench into modern cosmology. Were galaxies forming earlier than we thought? Is there a missing piece, perhaps an unknown force or particle accelerating structure formation? Could dark matter or dark energy behave in ways we haven't imagined? Or is there something even deeper, a fundamental flaw in our understanding of physics itself? Some researchers now propose modifying general relativity, introducing entirely new cosmological models, or even considering physics that operates differently under the extreme conditions of the early universe. The shock waves ripple far beyond astronomy. Theoretical physicists are back at their blackboards, questioning assumptions and retesting equations against this unsettling new data. The implications stretch into philosophy too. If our understanding of the universe's birth and growth is incomplete, what else might we have misunderstood? Are there cosmic epochs forever beyond our reach? Could there be layers of reality we've never looked for simply because we assumed they didn't exist? It has given us data that threatens to overturn the very principles used to interpret it. The ramifications touch every corner of astrophysics, stellar evolution, black hole growth, dark matter, the cosmological constant, even the nature of time and space. Already research teams are racing to verify the findings. If they hold, this may become the most significant paradigm shift since the discovery of the expanding universe. This is not about explaining away a few anomalies. This is about the scaffolding of the cosmos itself. Perhaps we've underestimated the forces at play, or overlooked critical variables that shaped history faster than we thought possible. Some even question whether time flowed differently in the early universe, whether density, gravity, or quantum effects warped its passage in ways that changed what 300 million years truly meant. Others suggest that dark energy behaved differently back then, or that black holes formed directly from density fluctuations, seeding galaxies earlier than thought. Whatever the explanation, Webb has opened a door that cannot be closed. The questions it raises demand answers, even if those answers require rewriting physics itself. It is a terrifying and exhilarating time for science. Terrifying because so much of what was assumed certain is now in doubt. Exhilarating because such moments of disruption often precede leaps in understanding. The telescope continues its vigil in the cold vacuum of space, gathering light that may rewrite textbooks and redefine what it means to know the universe. Its discoveries have shown us that the cosmos is stranger, more dynamic, and more mysterious than we ever believed. It has reminded us that vast unknowns still await us, and that our drive to look deeper, farther, and to question everything, must evolve as fast as the universe itself. Got it? Here's your text rewritten in a similar style to the K218b1 you liked earlier, flowing like a narration without headings or hash marks. Dark matter has always been the invisible glue in our models, the unseen scaffolding that explains why galaxies form and hold together. But Webb's latest discoveries are complicating that picture. Galaxies are appearing earlier, larger, and more complex than expected. If this is real, then maybe dark matter isn't as simple as we imagine. Perhaps it interacts more than our models allow. Perhaps it clumps together faster. Or maybe the entire paradigm of cold dark matter is flawed, replaced by something stranger, warm, self-interacting, or even an entirely new form that rewrites the rules of cosmology. And dark matter isn't the only suspect. Some physicists now wonder if these galaxies are the fingerprints of hidden laws of physics that only operated in the early universe, particles that have since vanished, extra dimensions that briefly revealed themselves, or even modifications to gravity itself. Bold theories once pushed aside as speculative, variable speed of light, scalar field cosmologies, cyclic universes, are suddenly being revisited with renewed seriousness. What was once fringe might now be necessary. But here's the tension. We already have a snapshot of the infant cosmos, the cosmic microwave background, a delicate afterglow frozen when the universe was only 380,000 years old. That data, recorded by COBE, WMAP, and Planck, paints a precise picture of density, temperature, and uniformity. And yet Webb is now showing us massive, structured galaxies appearing far earlier than the CMB would suggest is possible. Two datasets, each stunningly accurate, but seemingly in conflict. Reconciling them may be the hardest challenge modern astrophysics has ever faced. What makes this even more profound is the human element. For centuries, our understanding of the universe has grown through crises like this. Each great leap forward, heliocentrism, relativity, the Big Bang, was born when observation broke theory. Perhaps we are living through another such moment now, when our cosmic story fractures just enough to reveal a deeper truth. These galaxies aren't just glowing smudges of ancient light. They are messages carried across billions of years, arriving now to shatter our certainties. The implications ripple beyond science. Particle physicists, cosmologists, quantum theorists, and engineers will all need to work together, crossing the boundaries of their fields. New models must be tested. New instruments must be built. Even our assumptions about time may be wrong. Some physicists suggest that in the extreme energy of the early universe, time itself may not have flowed as we understand it. Perhaps it fractured, stretched, or layered upon itself, allowing galaxies to mature along pathways that defy linear chronology. If that's true, then our most trusted laws may be statistical illusions. Rules that hold in most places, but not everywhere. And then there's the larger possibility that what we are seeing isn't even the story of this universe alone. If early conditions allowed regions of space to evolve under different rules, then we may be glimpsing evidence of a multiverse, a cosmic landscape where physical laws vary, where universes bloom and decay under different rhythms. These ancient galaxies could be the fossils of that deeper tapestry, proof not of a singular origin but of a layered reality. What if the Big Bang wasn't a beginning at all, but a transition? Conformal cyclic cosmology, quantum loop models, and other bold frameworks propose that our universe may have inherited patterns from a prior reality, passing them forward across cosmic rebirths. If that's the case, then Webb's galaxies are not just early structures. They are echoes, memories carried across time from universes before ours. The Webb telescope is only just beginning its mission, and already it has given us mysteries that threaten to unravel our neatest equations. Future observatories, the Roman Space Telescope, the extremely large telescope, and Webb's eventual successors, will probe even deeper, perhaps detecting the whispers of particles long vanished or gravitational waves from a time before stars existed. But even now, the message is clear. The universe is not just more complex than we imagined. It is stranger. Stranger than our equations, stranger than our philosophies, stranger than the stories we've told ourselves since the dawn of time. These galaxies, impossibly ancient and impossibly vast, remind us that the universe has secrets it will only reveal when we are ready to listen. And as Webb gathers more light, more whispers from the deep past, it feels less like we are looking into space and more like space is looking back, inviting us to rewrite not just our models, but our place within them. So the question is no longer whether we will accept this shift. It is whether we are prepared for what comes next.